In Chapter 1, we introduced the concept of internal energy as being made up of the energy of each particle. And we said that this energy was made up of translational energy, rotational energy, vibrational energy, and electronic energy. So it's important that we understand the energy associated with each of those motions. What we're going to find, and you already know this to some extent from freshman chemistry, is that the energy is quantized. But why is the energy quantized? Let's start with a system that we're familiar with. You remember studying the hydrogen atom in freshman chemistry. Our study of the hydrogen atom led us to understand that the energies were quantized. So the electron in the hydrogen atom could only take on certain energy values. And we labeled those energies with quantum numbers. So n equals 1 was the lowest energy, n equals 2 was the next highest energy, and so forth and so on. These quantum numbers are simply indexes for each of the energy levels. You will recall that there was only one way to make the n equals 1 state, and we called that 1s. However, there were 4 ways to make the n equals 2 state, and we called those 2s, 2px, 2py, and 2pz. Likewise, there were 9 ways to make the n equals 3 state, and 16 ways to make n equals 4, and so forth and so on. So there were n squared ways to make each state. When we have more than one way to make a particular energy, we say that that energy is degenerate. And the degeneracy is simply the number of ways that we can make the state. The lowest energy state is termed the ground state. The higher energy states are called excited states. So now that we know some of the terminology associated with quantum states, let's take a look at why these energies are quantized. Quantization of energy is a direct consequence of wave-particle duality. Recall the Einstein-de Broglie relationship, which says that any moving particle has a wavelength associated with it, which is related to the momentum of that particle. Likewise, a wave has a momentum associated with it according to its wavelength. To see how this leads to energy quantization, let's imagine trapping a particle in a box. This is the well-known particle in a box problem. So we'll take a box and we will stick our particle in that box. So the particle can't get out of the box. It has to stay in the box. How can I trap a particle in a box? Well, in a sense, we've trapped our electron in the hydrogen atom in a spherical box because of the Coulomb attraction between the electron and the proton. That Coulomb attraction, that potential energy, that force, requires that the electron stay close to the nucleus in a spherically symmetric box, as it were. I could also imagine trapping a negatively charged particle in a box by placing a negative charge on either side of it. Then, when the particle runs into that negatively charged wall, the Coulomb repulsion forces the particle to stay within the two negatively charged walls. More generally, I might take a particle, which could be neutral, and put on either side of it a wall with a very high potential energy. If that potential energy is infinity, then no matter how much kinetic energy my particle has, it cannot overcome the infinite potential energy on either side of it, and that confines my particle to this region in space. This is the construct that we will use to examine the particle in a box. Now let's remember that our particle is actually a wave. So I really need to draw this particle not as a point, but as a wave in my box. If the length of my wave is such that it does not have a node at the walls or doesn't fit in the box, then the reflected wave is going to be out of phase with the wave. And what's going to end up happening is that all the reflected waves are going to destructively interfere and create no wave in the box. If I have no wave, I have no particle. Thus, the particle exists in the box only if its wavelength is half integer multiples of the size of the box, the length of the box. So n is simply an integer, and when n is 1, we have a half a wavelength in the box. When n is 2, we have a full wavelength in the box. When n is 3, we would have 1.5 wavelengths in the box, and so forth and so on. So this implies that our wavelength has to equal 2 times the length of the box divided by an integer n. So only certain wavelengths are possible. And if only certain wavelengths are possible, only certain momentum are possible. Since the momentum is equal to the mass of the particle times its velocity, we can solve for the velocity, which will equal n times Planck's constant divided by 2 times the mass of the particle times the size of the box. The energy of the particle is all kinetic energy, and so it equals 1/2 mv squared. And therefore, the energy of the particle is equal to n squared h squared over 8 ma squared, and the energy depends on the quantum number n. So only certain energies are possible because only certain values of n, 1, 2, 3, so forth and so on, are possible. So in general, any particle confined to a region in space by a potential will have quantized energies. Let's take a little bit closer look at the energies of the particle in a box. So the energies depend on the quantum number n, and far apart are any two given energies. So let's look at the n plus 1 level and how far away it is from the nth level. So if we put n plus 1 in for n and subtract that from what we get when we put n in for n, we find, doing the algebra, that the difference in energy between any two given n levels is 2n plus 1 divided by 8 ma squared. So we'll write that as delta E n plus 1 to n is equal to 2n plus 1 h squared over 8 ma a squared. What's interesting about this is that the energy levels get further apart the higher n is. So for our n equals 1 level, which is our ground state, it's a small distance away from n equals 2, but n equals 2 is further away from n equals 3, and n equals 4 is even further away from n equals 3. This results from the fact that the change, the difference between energy levels, depends on n and gets larger as n gets larger. Notice that if the difference between energy levels is very, very small, smaller than I can measure, then we essentially have a continuum of energy levels. In other words, each energy level is so close to the next one that it appears as though I can access all possible energies. This is just the classical case. So let's look at what conditions would make my change in energy very, very small. Notice that the larger the mass, or the larger the size of my box, the smaller my difference in energies. So as the mass increases, the difference in energy decreases, and as the size of my box increases, the difference between energy levels decreases. So we say that as the mass increases, or the region in space where my particle is confined, or the size of my box increases, my particle behaves more classically. It goes towards the classical limit. And that is why large particles, such as baseballs, we don't have to consider as having discrete energies.